Okay, so we continue. So now we look on the how we can get what we call as the value for the active and passive pressure. Okay, based on the what we call as based on uh, the first derivations of the theta fan. Okay, so in an undrained material, okay, so the stress conditions in zone 1 are still represented by the more circle in 11.2b. Okay, so you need to go back, okay, on our previous discussion, uh, 11.2b, because I not put the, okay, okay, this is 11.2b. So put in your put in your put the notes on that 11.2b is at your slide number 42. Okay, so this is 11.2b. Okay, so then for the more column, okay, circle for zone 2 is shown in figure 11.7a. Okay, so this is for the more column for the zone number 2. Okay, so the for the active case, when the soil is in zone 2 is at the plastic failure. Okay, so the major principal stress, okay, sigma 1 acts on the plane which is rotated by 2 theta equal to pi minus A2, okay, from the stress plate on the wall, which is itself at the angle W to the vertical. Okay, as sigma 1 is the zone zone 1 in vertical, the rotation in the principal stress directions from zone 1 to 2 is theta fans equal to sigma 2 over 2 minus W. Okay, from figures 11 from figure 11.17. So the magnitude of the S1 reduced moving from zone 1 to zone 2. Okay, so then this is the what we have discussed before, which is the 2 CU, okay, theta fans. Okay, so we look on the derivation. Okay, okay, so this is for the undrained, for the rough wall. Okay, how we determine the theta fan, okay, if there is what we call as a uh, better angle, where we include the better angle as well. Okay. Uh, how this value is obtained? Okay, so you look on the derivation. Okay. This is considered as 90 degree. Okay. So pi over 2 is 90 degree is equal to theta fan plus theta plus W. Okay. So then we rearrange, okay, in order to get what is the theta fan. So the theta, okay, is equal to pi minus theta delta 2 over 2 as we have discussed before. Okay, or we refer to this approach, okay? where from the more column to a normal diagram, so we should divide it two. Okay, so then we obtain theta is equal to pi minus delta 2 over 2. Okay, so then include this theta inside this equation. Then later on, we obtain the theta fan is equal to delta 2 over 2 minus W. Okay. Okay. So this is how the value has been derived. Okay. So from there to S1 minus 2S2, then we obtain 2Cu theta fan. Okay. Okay. Uh, our theta fan, uh, we put the theta fan inside this equation, okay, as theta 2 over 2 minus W. Okay. So later on, we obtain, okay, 2, okay, 2, we obtain 2 delta 2 minus 2W. Okay. So in zone 1, okay, S1 is equal to then sigma B minus Cu. Okay? So in zone 2, the total stress acting normal to the wall from figure 11A is given by EA is equal to S2S minus 2 minus Cu cos delta 2. Okay. So look on the derivation. Okay. Okay, to get the PA, okay, uh, okay, this is S2 minus S1 equal to 2 CU theta fan. Okay, then the theta fan should be included in the uh, the value sorry the value of the theta fan should be included in this value. Okay, then we obtain the S1 is equal to effective stress minus Cu. Okay, okay. So for the PA, okay, is equal to S2 minus Cu delta 2. Okay, let me check first the PA part. Okay, so then this is the equations, okay, to obtain what we call as the active uh, pressure, okay, uh, for case of the undrained, uh, where we consider the what we call as the wall roughness, and also consider what we call as the uh, better angle. Okay, so later on I will show. I will try to find any example. Okay, that related to the what we call as to on the use of the equations. Okay, so because on the next slides, okay, there we show the procedure. Okay, uh, when we deal with this kind of problems. Okay, so we may use the last equation, okay, to determine the force, okay, based on problems. Okay, okay, okay. In this procedure, okay. So that is the derivation for the equations uh, for the active undrained conditions. Okay. So now for the passive part, okay. So the more circle for the zone 2, okay, is shown in 11.7b. Okay, so this is the for the passive one. Okay, sorry, I have not derived it yet. Okay, okay, but I will explain this on this diagram. Okay, so for the passive part, okay, on the wall represent the stress in the vertical directions. Okay, so the major principal stress delta 1 acts on the planes which is rotated by 2 theta equal to delta 2. Okay, because for the passive, okay, the horizontal effective stress is considered as delta 1. Okay. So based on the more column diagram, the two the delta 2. Okay. So from the stress state of the wall, which is itself an angle of W of the vertical. Okay. So as sigma 1 in zone 1 was horizontal, the rotations in the principal stress direction is theta fan, which is theta with delta 2 over 2 minus W. Okay. The magnitude of the S1 increased moving from zone 1 to zone 2. Okay. So then the CU is delta 2 minus 2W. Okay. So in zone 1 from figure in slide 42 or in 11.8a, okay, S1 is equal to sigma V plus Cu. Okay. So then in zone 2, the total stress acting normal to the wall from figure 11.7b is given by equation 11.18. Okay. So S2 plus Cu cos delta 2, okay, shall be used if we want to get what is the passive horizontal effective stress. Okay. Okay. So from figure 11.7, it is clear that, okay, the sine delta 2 is equal to tau over Cu or alpha. Okay. So in that case, to determine the active or passive earth pressure acting on a given wall, the following procedure should be followed. Okay. So find the mean stress in zone 1 from equations 11.14 or 11.17 for active or passive condition respectively. Okay, so then we look on the equation 11.14. Okay, this is the equation of 11.17 for the passive and active. Okay, determine delta 2 from equations 11.19. Okay, find the mean stress in zone 2 from equation 11.13 and 11.16. Okay, so from there we can estimate the earth pressure using equation 11.15 or 11.18. Okay, so this is a procedure that we need to follow, okay, in order to solve for the handling soil types. Okay, if we deal with rough angle, a rough soil, rough wall, and also so said also if there is a better angle of the wall. Okay. Okay. Okay, this is for the dream case, eh? Okay. So I guess for the next meeting, okay, I will try to find an example, okay, on how to use the equations or the procedure. Then it can help to get a better understanding. Okay. And I also try to derive the equation. Okay. because it's very time consuming. Okay. Whereby I need to look again on the advanced mathematical equation to uh, to to derive the equations. Okay. Otherwise, we only understand uh, how the derivation work. Uh, Hard to understand without any derivations. Okay. Although we have derived, so it's complicated as well. Okay. 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 So I mean that um, for the undrained case, okay, you need to make a simple notes. Okay, we will not go in detail for derivation. We just use the equation. Okay, so then make a simple notes. Okay, what is the equation 11.14, 11.17? Okay, so what is the delta 2? Okay, then what is the S2 for the zone 2? Okay, equations. The last one, put all the equation inside the previous equation to determine the PA and PP. Okay. Okay, I will try to find any example for the next meeting. Then I will show with you in detail how the process works. Okay. Okay. For the drain case, I didn't have the equation, the derivations. Okay. So we just go through first. Okay. Later on, I will try my best to provide the derivation. Okay. Okay, similar for the drain case, we need to determine how to change from the principal stress, rotate from zone 1 to zone 2, okay, and includes the phi value, because for the drain case, we have a phi value, okay. Like in the undrained case, let's consider the principal stress rotation across one frictional stress discontinuity, okay. The same approach where we have a stress discontinuity line, then this is the principal plane in zone 1. This is the principal plane in zone 2. Okay. So then we look on the Moore circle diagram. Okay. So this is a Moore circle diagram for drain case. Sorry, for the drain case without having any C value. Okay. Since we are dealing with drain material, the maximum strength is tau equal to sigma tangent phi by neglecting the coefficients. So the average effective stress is assumed to increase from zone 1 to zone 2. So then the Moore circle are tau equal to sigma tangent delta. Okay. So this is the Moore circle diagram. Okay. Okay, the same approach that we need to have ABC to get the delta. Okay, so then we need to use get the angle. Okay, then this Moore circle diagram we put inside this this diagram, okay, to get what is the theta fan. So it's better to have in hand the diagram because uh, we need to go for the explanation time. We need to look on the diagram. Okay? For example, figures 7 show the more circle intersect at the point C. Okay, so look on the diagram and look on this statement. Okay, so where is the point C? Point C is located here. Okay, so this is a state on discontinuity. Okay, because between zone 1 and zone 2 is happened here. Okay, where the sigma stress and tau must be the same to maintain the condition of equilibrium. Okay, point C in the position of frictional discontinuity. Okay, figure 6 and 7. A linear line similar to the failure envelope. Okay. T maximum. Okay, that is the maximum value. Sigma tangent phi is drawn from the original point from the original to point C. Okay. In figure 7. Okay. So the mobilized. Okay, then we need to draw the maximum, okay, to identify what is the mobilized friction angle and the discontinuity. Okay, so in this case, okay, so this is the line that need to be drawn, and it should intersect the point C. Okay. Okay. So let angle ABC is delta. Okay. This means that the position of the C, position of the friction is delta plus, so the other one also called delta. Okay. Let uh, from the Google. Okay. So what is the so good letter? Okay, both of them are delta. And delta. Okay. So let me see delta. Okay, this means that the position of C, position of the friction derivative is also delta plus delta. Okay, as in figure 7, and delta plus delta over 2 in figure 6, counterclockwise for the major principal plane of zone 1. Okay, so then we look on the this, so we present this one. Okay. So where we get that one, okay, we look on the more column diagram. More column diagram, okay, here. It happening here. Okay. So it's a delta plus delta. Okay. Because this also considered as delta. This is delta. So this value is also is a delta. Okay. All right. Okay. So if you derive further the point C, okay, so then for another point C, okay, is delta plus P minus delta counterclockwise from the major principal planes, okay, in in vertical sorry, in zone 2 in figure 7. Okay, this is equivalent to delta plus pi minus delta over 2 counterclockwise. Counterclockwise. Okay. So then we look on this angle. Okay, so it is pi minus delta plus delta in the more column. So in the actual is a delta plus pi minus delta over 2. Okay. So that is for the, then later on we can get the theta value. Okay. So therefore, okay, the major principal plane angle of rotation from zone 1 to zone 2 is equal to theta equal to pi over 2 minus delta. Okay. So then we try to get okay the ratio between the S1 DC, okay, where the DC is equal to T1 sine delta plus delta, okay. Then consider again the triangle S2DC, which is the DC is equal to T2 sine delta minus delta, okay. So then get the what we call as the ratio T2 over T1, okay. Then it become S2 sine theta over S1 sine theta, okay. So the theta used here, okay, we can change into delta plus delta, okay. Then includes this equation, okay, rearrange pi over 2 plus delta, okay, put inside, replace the delta there, okay, then we get this equation. Then use what we call trigonometric identity, okay. So then we get this value. Okay. So for super small principal plane rotation, d delta, the increase S1, S2 is also super small. Okay. So delta is equal to 90 and S equal to phi. Okay. Which is the T maximum is mobilized. Okay. So then S2 over S1 is S plus ds over S equal to cos minus d theta over cos pi minus d theta. Okay. So by using another trigonometry identity, okay, so then we get okay, then the d theta is considered super small. Okay, then we simplify it later on. Then we obtain 1 plus ds over s cos pi plus sine theta sine d delta and d theta over cos pi minus sine theta sine d. Okay, dividing the top. Okay, dividing the top and the bottom, especially on the right side, by cos phi. Then using the binomial expansions, okay, 1 plus x power by n approximately equal to 1 plus nx. Okay, if n is very small, okay, 1 plus ds over s equal to 1 plus tangent phi d theta times 1 minus tangent phi d theta power by -1. Okay, then it simplified to get 1 plus theta d pi d theta and d theta. Okay, then ds over s is equal to 2 tangent phi d theta for total rotational throughout sea of frictional discontinuity with angle key. So then S2, S1, ds over s, okay, 2 tangent, integrate theta fan over 0. So then we obtain ln S2 over S1 equal to 2 tangent phi theta fan. So S2 over S1 is equal to E epsilon 2 tangent phi theta fan. Okay. So that is for the derivation of the theta fan. So are we go later on, okay, on the full derivation. So it's very time consuming. Okay. I unable to do it for this case. Okay. For the previous one, I have did it. Okay. Then, but for this case, okay, we just go through and then later on I will share with you. Okay. Yeah. Okay, then we work again. Okay, the same procedure. Okay, to get the full derivations. Okay, for the PA and PP. Okay, so for this, okay, we should know that the more circle for zone 1 in the active and passive side remain as same as in figure 7. Okay. The figure for the undrained case. Okay. The more column for zone 2 is drained is shown in 11.8a. Okay, so then we refer to this what we call this diagram. Okay, to do the same procedure with the one that on the undrained. Okay. So for the active case, when the soil is in zone 2 is at the plastic failure, the major principal stress sigma 1 acts on the plane, which is rotate 2 theta equal to pi minus delta 2 minus delta from the stress state on the wall, which is itself at the angle of W to the vertical. Okay. So the sigma 1 in zone 1 is vertical. The rotation in principal stress direction is theta fan, has been derived before, okay, in figure 11.8a. That is for the zone 1. Okay. The magnitude of the S1 reduced moving from zone 1 to zone 2. Okay. 11.8a is not for the drain, it's for undrained. This one. Yeah, I need to look again. Wait. So you got 11.88 is yeah, okay, 11.88, sorry. This is for the active. Okay. So then we need to use the same approach, okay, where we need to find what is the delta, okay, what is the delta fan based on this. Here are we better? Okay. The magnitude of the S1 reduced moving from zone 2, okay. So this is square fan. Okay, so where we get this one, we have derived before here. Okay. So then the theta fan, okay, 11.20. Okay. So in zone 1, figures in slide number 43. So look on the slide number 43 for the drain case. Okay, here. Okay. So then the S1, sorry. Okay. Okay, so the S1 is equal to sigma V over 1 plus sine phi. Okay. So this is for the 11.8. Okay, in zone 2, the effective stress acting normal to the wall from figure 11 11.8 A is given by S2 minus S2 sines P cos delta 2 minus delta. So then we simplify that S2 times 1 minus sine P cos delta 2 over delta. Okay, then defining the active earth pressure coefficient in terms of the normal rather than horizontal effective stress as the wall is battered by W. Okay, so then we obtain the equation of Ka as stated in 11.23. Okay, so that is for Ka. Okay. Wall. Okay. So then for the Mohr circle for zone 2 is shown in figure 11.8p for the passive case when the soil in zone 2 is at the plastic failure. Okay, the major principal stress sigma 1 act on the plane which is rotated by 2 theta equal to delta 2. So this is the delta 2, not 2. So this is subscript plus delta from the stress state on the wall, which is itself at an angle of W to vertical. Okay. As sigma 1 in zone 1 is horizontal, the rotation in principal stress direction in theta fan. Okay, also delta subscript 2 plus delta over W minus W over 2 minus W. So the magnitude of the S1 increase moving from zone 1 to zone 2. Okay. So then it becomes 0.24. Okay. And in zone 2, we obtain 11.26. Okay. For the normal stress. Then the Kp, okay, is derived based on the equation 11.27. Then 11.28 is the sine delta 2 equal to sine, it's sine delta 2 equal to sine delta over sine phi. How to get the delta 2? Okay. So this is the procedure, okay, to determine the active or passive earth pressure for a given wall. The following procedure should be followed, okay. First, determine the effective find the vertical effective stress in zone 1. Determine delta 2 in these equations. Find the earth pressure coefficients from equations 11.23 for the active, okay. While for the passive, 11.28, 11.27. Okay. Okay, then evaluate the earth pressure using equation 11.6 or 11.8. 11.6. Okay. It's 11.6. 11.6. Yes, 11.6. Or 11.6 is the one that we normally calculate for the effective. Okay, this one. This is 11.6 and 11.8. So please write down this is 11.6. Yeah, I will remove it on page uh, 46 millimeter. Okay, with the, at the pitch of at the pitch of 46. Okay, so here at the pitch of 44, hmm? 44 and 43. Hmm? 43. So you please write down 44. Okay, so that this is for the drain problems. Okay? Okay, can we take 5 minutes? Okay, as I later on, I will show the full derivation. Okay, the first part is to determine the theta fan. So from the theta fan, we need to work out to determine the PAP. Okay, so from PAPP, we need to go through the procedure, okay, to get what is the PA and PP, okay, for that kind of case. Okay, 5 minutes break. I want to go to toilet first. Okay. Okay, we continue on the wall sloping backfill. Okay, so it means that on the top of the wall, on the top of the backfill, there is okay. So again, okay, later on I will show the derivation. Okay, so we just for today we just familiarize with the some of the equations, okay, for the these problems. Okay. Okay, in many cases of the retained soil behind the wall may not be level, but may slope upwards at an angle beta to the horizontal as shown in figure 11A. Okay, so in this case, the major principal stress in the retained soil in zone 1 will no longer be vertical, and as the slope induce a permanent static shear stress within the soil mass, rotating the principal stress directly. Okay, directions. The stress conditions, normal and shear stress on the plane parallel to surface at any depth may be found by equilibrium as shown in figure 11.9a. So the component of the block self-weight W acting normally to the inclined plane per meter length of the mass is then this is the mass of one block on the top of the backfill. Okay. So then so we have identified the beta value. Okay. So gamma Z is the area, okay, based on per meter length, okay, so beta, okay, parallel to the plane. So then the tau mob, okay, the tau mob can be on this diagram, okay. The tau mob is equal to W over A sines beta, okay. Then we include the W inside the equations here. Later on, it becomes gamma Z cos beta sines beta. So considering equilibrium perpendicular to the plane, okay, which is the normal stress, okay, then the effective stress is equal to total stress minus U. Okay. So the total stress is considered as a normal stress, which is the W over E cos beta minus U. So then again include the W inside the this equation. Okay. So then we obtain gamma Z cos square beta minus W. Okay. Where U is the pore water pressure of the plane, okay, if the water is far, so there will be no issue of the U. So the stress condition in the retained soil may be represented by the stress ratio tau mobilized over effective stress. Okay, so then we obtain the tau, the tangent P mobilized value. Okay, so that is okay. So equation 11.3 apply for drain condition. For undrained condition where only total stress are required. So then the tangent beta is obtained. Okay? So then the same approach that we need to identify what is the tau fan, sorry, theta fan. So the more column for unconditional in figure 11, 10A. Okay, so this is the more okay. It can be seen that the major principal effective stress sigma 1 is rotated, okay, at 2 theta equal to theta 1 from the stress state. Okay, then you need to refer to the more column, more circle as well. From the stress state on the inclined plane in the retained soil, which is set at the angle of beta to the horizontal. Okay, so on the more circle, okay, so this is the beta and this is the value. Okay? The 2 theta. Okay. The resultant rotation of the principal stress in zone 1 compared to the level ground case is then theta is equal to sigma 1 over 2 minus beta. Okay. So as the result, okay, the theta fan, okay, is equal, should be modified to, okay, delta 2 over 2 minus W minus delta 1 over 2 minus beta. Okay, so when we can get the theta fan, here this on this diagram. Okay. So in zone 1, okay, from figure 1110A, okay, so 1110A here, this is 1110A. Is equal to sigma minus Cu cos delta 1. Okay, this replace equation 11.14. Okay, so we look again on 11.14. The difference in mean stress between zone 1 and 2 active for the general case for sloping meeting by a better graph is given by S1 minus S2 equal to Cu delta 2 minus 2W minus delta 1 plus 2 beta. Okay. So since since delta 1 is equal to T mobilized, tau mobilized over Cu. Okay. Equation 11.35 replace equation 11.13 for the case of sloping backfill and undrained condition. The solution procedure remains unchanged. Okay. So then the procedure we can follow the procedure for the okay. Then for drain, okay, for drain condition, in zone 1 issued in figure 11.10b, okay, it can be seen that the major principal effective stress is rotate 2 theta equal to delta 1 plus 5 mobilized here. Okay. From the stress of the inclined plane in the retained soil, which is itself at the angle of beta horizontal, the resultant of the principal stress in zone 1 compared to the level ground is then theta is equal to delta 1 plus 5 mobilized over 2 minus beta. As a result, the value of the theta fan, okay, theta fan modified to, okay, so this is the theta fan, okay, from figure 11.10b, okay, so sigma 1 is equal to S1 plus S1 P cos delta 1 plus beta. So then simplified into this cos, just simplified because this is S, so they put our S out, so then 1 plus sines P cos delta 1 plus delta. Okay? So later on, the KA, okay, from the these problems, okay, can be obtained as 11 based on the equation in 11.39. Okay, so sine delta 1 can also be looked on the 11.40. So that is for the sloping on the backfield. Okay. So KP, for the KP, okay, usually for the passive, it's not normal to have a sloping for the passive. So that's why it's only for the active. Okay. Normally for the passive, we use the flat because there is no what we call as a sloping on the backfield. Sorry, sloping on in front of the wall. Okay. Okay, then equation 11.10 replace the equation 11.23 for the case of backfill and drain. The solution procedure and all remain unchanged. So we change the 11.23. Okay, 11.23 before. Okay, then we put on this procedure. Okay, so this will be 11.39. So we can use the same procedure but with a different equation to solve for the drain on the backfield. Yeah. Okay, so this is the result as we have discussed before. Okay, how to determine the total thrust or check the overall stability of retaining structure. So the active and passive earth integrated over the height of the wall determine the resultant thrust, okay, which is used to define the horizontal actions. In the retaining wall structure is smooth, the resultant thrust will act normal to the wall. This may not be horizontal if the wall has the battered back. So for the case of retained, undrained, soil having uniform bulk density, combination of 11.35, 11.5, 11.45 gives 11.46A. Okay. While combining equation 11.16, 11.17, 11.18 give 11.46B. Okay. So equations 11.6, 11.46 is linear in Z, and this total pressure distribution are shown in figure 11.16. Okay. So this is on how we get the total thrust. As similar that we have discussed on the previous example, that we need to determine the area of the what we call of the problems based on the stress distribution diagrams. Okay. All right. Okay. That is for the unclear. In active case, PA is 0 at a particular depth from equation 11.46a with PA is equal to 0, so then we obtain the equation of 11.47. Okay, so this means that in the active case, the soil is in a state of tension between the surface and the depth Z naught. So in practice, however, this tension cannot be relied upon the act of the wall since cracks are likely to develop within the tension zone, and the part of pressure distribution diagram above depth Z naught can should be the total active thrust PA acting normal to the wall of height that with a better angle of relation of H and Z naught, P this over W. Okay. Not as we have discussed before that we consider one third if the diagram is in triangle. If the wall is rough, there is additional attraction force due to the interface acting downward along the wall of the same point. So then the equation of 6.11.48 changed to 11.4.9. Okay, where the tau W is equal to alpha CU. Equation 11.49 negates any interface shear in the tension zone above Z naught. Okay, it assume that the crack open between the soil and the wall in this zone. So the force at the distance of half H minus Z naught above the bottom of the wall. Okay. So for the passive case, it's always positive so that the total thrust acting normal to the wall of the height H is with a better angle of the wall W is PP dz over cos W. Okay. The two components of PP at a distance 1/3 H and 1/3 half respectively above the bottom of the wall as shown in figure 11:16. Okay, here 11:16. So this is for the PP. If the wall is rough, there is an additional traction, TP acting outward along the wall surface. In the case of drain, continuous material C is equal to 0, the lateral pressure acting on the retaining structure should be separated into the component due to the effective stress in the soil, and the component due to any pore water pressure, the effective thrust acting normal to the wall of height H with a better angle of W is shown in this 11.52A, 11.52B. Okay, and the resultant pore water pressure 11.53 because we differentiate between the effective and also the pore water pressure. Okay, so if the wall is rough, there will be an additional surface interface shear force acting downward along the wall surface on the active side and upward along the wall surface of the passive side. This is found using equation 11.51 on the active and passive side. However, the interface shear strength is tau W is equal to normal stress tangent delta. The normal and shear component of the thrust P and T are often combined into a single resultant force that acts at the angle of delta to the wall as shown in figure 11.17. Okay, this is for the drain case. Basically, the total thrust, okay, we need to draw the stress distribution diagrams, okay. So from there, we can get the area. From the area, that is the resultant thrust, okay. Okay, we look on this example. This will be our last example. Okay, calculate the total active thrust on a smooth vertical wall, 5 meter height, retaining a sand of unit weight 11 kilonewton per meter square, 8 meter cubes, for which P is equal to 35 and C is equal to 0. Okay? So the surface of the sand is horizontal and the water table is below the bottom of the wall. Okay, so that is A. B, determine the thrust of the wall if the water rise to a level 2 meter below the surface of the sand. The saturated unit weight of the sand is 20. Okay? So it is a flat wall, a vertical wall. So it means that, and it is smooth. Okay? So W is to represent the better angle. Delta is represent the smooth. Beta is represent the slope. So all of the parameter is 0. Okay. So then to solve the problems, okay, we may use the simple one. Okay. If you want to use the complicated, okay, if you want to try, okay, use this complicated equation. What is the backfill? This one. Okay, try to use this equation. Okay. I guess you also will get almost the same with the simple one. Okay. You can use 11.39, the complicated equation, 11.23, that doesn't have any slope, and 11.5, that the wall is smooth, no better angle, and also no slope. So the Ka is equal to 0.27. Okay. So with the water table below the bottom of the wall, okay, so means that it is a dry. Okay, so then you use the sand unit weight of 17. Okay. So based on the equation 11.52a, our previous discussion of the total resultant 11.4, okay, this one. Okay. So still cos W is 1, it's 0. Okay, cos W is 1, 0. Cos 0 is 1. Okay. So with the water table below the bottom of the wall, okay, so then Ka dry, okay. So a simple one, okay, where the half times Ka times 17. Okay, half time Ka times dry times H square. Okay. As I mentioned before, it's a single type of material. Okay. So this is will be gamma H. So this is will be your H. So then HA for the to get the horizontal. Okay, so then we obtain 57.5. Okay. That is for the A. The class of the wall, if the wall table rise to me below and the settlement we have go through before. Okay, so we need to divide into several layers. Okay, so this is very tedious. It's better to use a simple approach. Okay, we use what we call as the first, okay, get the second, then get the third, okay. So yeah, the result will be same, okay. So PA is 9.2 for the first area, P2, PA2 is 27.6, okay. The third area is 12.4, okay. So they use the unit weight of water 9.81, and then the last one is 9.81 times 3 square times half, so 44.1. So then the final result is 93.3. Okay, so that is for the to get the total trust. Okay, okay, based on the approach from NAPED textbook. Okay, I guess we stop until that. Okay, because this is based on a column approach. Okay. Okay. Next week I will uh, give you the derivation. Okay. Then we good. We will go through in very fast. Okay. Then I will show one or two more example. Okay, based on the derivation or based on the equation for the slope, the angle, and also for the rough. Okay. Then we will continue for the next lecture. Okay. By starting from the column theory of okay, until we complete it. Okay. Okay. So that's all for today. Okay. A little bit early because it's very uh, complicated discussion. Okay. And require a lot of me to think. Okay. Okay. Any question before we end?
Sir,
Ah.
is it confirmed that we going to have a test on the 8th of February?
Yes, yes. I need to follow for the schedule.
And also, when are we going to do the revision for that one?
Oh no, yeah, it's not necessary for revision. I will tell you which part that I will ask you.
Oh, okay.
Okay.
How many question will the paper consist?
Usually two. Okay, the first one may involve the derivation. The second one may involve the calculation.
Okay.
We concentrate only on the Milo one. Milo one more,
Okay, Milo one.
but I better for on the lateral stress first. Okay. Okay.
Okay. Okay.
Okay. Okay. Okay, that's all for today. Okay, thank you very much. Okay, we will meet next week. Okay.
Thank you, sir.
Assalamualaikum.
Thank you, sir.
Waalaikumsalam.
Good afternoon. Okay,
Salam,
bye-bye.
sir. Thank you.